Tonight, we're going to ask the most dangerous question in science. Not dangerous because asking it will harm you. Not dangerous because the answer threatens anyone's safety. Dangerous because the question itself attacks the foundation of every assumption you carry about reality, about time, about existence, about what it means for something to be. What existed before the Big Bang? Most people, when they first hear this question, assume the answer is nothing, a void, emptiness, a blank. The universe exploded into existence from nothing, and before that, there was nothing. And nothing is what the word nothing means. But that answer is wrong. Or at least, it is far more complicated than it sounds. Because nothing is not as simple as it seems. Because before turns out to be a word that may not survive contact with the physics of the earliest moments of the universe. Because the question of what came before the Big Bang leads you, step by step, through some of the most revolutionary and most disturbing ideas in the history of human thought. And the answers that physics and cosmology have produced are not simpler than nothing. They are stranger. They are larger. They are, in every meaningful sense, more terrifying. By the end of tonight, you will understand what the Big Bang actually was. What happened in the first instance of the universe's existence? What our best theories say about what might have come before? And why each possible answer raises questions more profound than the one it answers. You're going to walk through inflation, through the multiverse, through eternal inflation, through the cyclic universe, through quantum cosmology, through the possibility that time itself had a beginning, and through the deepest and most honest answer physics has to offer. And that answer is not nothing. It is something that the word nothing was never equipped to handle. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Let's start by correcting a misconception so widespread that it appears in textbooks, in documentaries, and in the explanations of people who should know better. The Big Bang was not an explosion. When most people hear Big Bang, they picture something like a bomb going off in empty space, a fireball expanding outward through a pre-existent void, matter and energy blasting outward from a central point, filling the darkness with light and heat. A dramatic, violent beginning in an otherwise empty universe. None of that is correct, and the misunderstanding is not just a minor imprecision. It fundamentally misrepresents what the Big Bang was, and that misrepresentation is what makes the question of what came before it seem simpler than it is. The Big Bang was not matter and energy exploding outward through space. The Big Bang was space itself expanding. Space, time, matter, energy, and the laws of physics all emerged together in the Big Bang. There was no pre-existing space through which anything exploded. There was no pre-existing time in which the explosion occurred. Space and time themselves began in the Big Bang. Or at least, the space and time we inhabit began there. This is the central insight of the general relativistic cosmology developed by Einstein, Friedman, Lemaitre, and others in the first decades of the 20th century. The universe is not a collection of matter embedded in a fixed background of space and time. Space and time are dynamic. They expand, they contract, they curve. They are participants in the physics of the universe, not passive backdrops. The expansion of the universe, observed directly by Edwin Hubble and his collaborators in the 1920s, is not galaxies moving outward through a fixed space. It is the space between galaxies stretching. New space being created everywhere simultaneously. Galaxies being carried apart from each other, not because they're moving through space, but because the space between them is increasing. Running this expansion backward in time, you reach a moment when all of space was compressed to an extraordinarily small region. All of space, not a point in space. All of the space we can observe, and possibly all of the space that exists, compressed into a volume far smaller than an atom. The density of matter and energy in this compressed state was effectively infinite. The temperature was effectively infinite. The curvature of space-time was effectively infinite. This compressed state, this singularity, is what the Big Bang describes the emergence from. The universe did not emerge from the Big Bang. The Big Bang was the beginning of the universe's evolution from that initial compressed, hot, dense state into the cool, expanded, structured universe we inhabit today. And here is the problem with asking what came before it. Before is a word that presupposes time. To ask what came before some event is to assume that there was a time before that event. But if time itself began at or near the Big Bang, then asking what came before the Big Bang is like asking what's north of the North Pole. The question sounds grammatically valid. It has the form of a meaningful question, but it may be asking for something that doesn't exist, not because the answer is unknowable, but because the question is malformed. Because it uses a concept, before, in a context where that concept doesn't apply. Whether time truly began at the Big Bang, or whether there was some form of time before it, is one of the deepest open questions in physics and cosmology. And the different possible answers lead to very different stories about what the universe's origin means. Let's talk about the singularity itself. Because the singularity is where the question of what came before gets its teeth. In general relativity, a singularity is a point or region where the mathematical quantities used to describe space-time, the curvature, the density of matter, the energy density, diverge to infinity. The equations produce results of infinite magnitude. Division by zero. Physically meaningless predictions. The Big Bang singularity is predicted by running the equations of general relativity backward from the observed present state of the universe. As you run time backward, the universe contracts. Galaxies approach each other. The cosmic microwave background radiation, the faint glow of thermal radiation that fills all of space and was released when the universe was about 380,000 years old, becomes hotter and more energetic as you run time backward. The density of matter increases. The temperature increases. Eventually, in the earliest moments of cosmic time, the density and temperature diverge to infinity. The mathematics breaks down. This breakdown is telling us something important. It is telling us that general relativity, our best and most thoroughly tested theory of gravity and space-time, is not a complete description of reality in conditions of extreme density and curvature. General relativity works extraordinarily well across an enormous range of conditions. It has been tested in the solar system, in binary pulsars, in gravitational wave events, in the structure of the observable universe, and in every test it has passed with extraordinary precision. but it was never designed to handle conditions where quantum mechanical effects are important. And in the extreme density of the early universe, quantum mechanical effects are crucial. We don't have a complete theory of quantum gravity, a theory that combines general relativity's description of space-time curvature with quantum mechanics' description of matter and energy at the smallest scales. Without this theory, we cannot reliably describe the earliest moments of the universe's history, precisely the moments when the question of what came before becomes most acute. The Planck time is the moment before which our physics completely breaks down. It is approximately 5.4 times 10 to the minus 44 seconds after the Big Bang. A decimal point followed by 43 zeros, and then a 5. 1/10,000,000 trillion trillionth of a second. Before this moment, the universe was so dense, and the curvature of space-time so extreme that quantum gravity effects dominate, and our current theories tell us nothing meaningful. The cosmic microwave background, which is our most direct observational window onto the early universe, was released when the universe was about 380,000 years old. The observations by the COBE, WMAP, and Planck satellites of this radiation are among the most precise in cosmology. And they have confirmed the Big Bang model in remarkable detail. But 380,000 years is an enormous distance in time from the Planck era. Between the Planck time and 380,000 years, we have a progressively better theoretical description, supported by observations of the light element abundances created in Big Bang nucleosynthesis in the first minutes, and by the physics of the quark-hadron transition and the electroweak phase transition at fractions of a second. But before the Planck time, we have nothing reliable. The singularity predicted by general relativity at time zero is almost certainly not a literal physical feature of the universe. It is almost certainly a signal that our theory breaks down before we reach that point. Just as the singularity predicted inside black holes by general relativity is almost certainly a failure of the theory, rather than a real physical infinity. A complete theory of quantum gravity would likely replace the singularity with something finite, something that can be described, something that has a before. What that before looks like is the deepest question in cosmology. Before we explore what might have preceded the Big Bang, we need to understand what we know about the very early universe. Because the earliest moments of the universe's history contain clues, fingerprints, signatures of whatever came before or whatever gave the Big Bang its initial conditions. In the first fractions of a second after the Planck era, the universe underwent a sequence of phase transitions that determined the fundamental properties of the universe we inhabit today. These transitions are called phase transitions because they resemble, in a formal mathematical sense, the phase transitions of ordinary matter. The change from liquid water to solid ice, or from liquid water to steam. In these cosmological phase transitions, the symmetries of the laws of physics changed as the universe cooled. At very high temperatures, the laws of physics that govern matter and energy looked different from how they look today. The four fundamental forces that we know, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are believed to have been unified at sufficiently high energies. As the universe cooled, they separated through a sequence of symmetry-breaking transitions. The electroweak phase transition occurring at about 10 to the minus 12 seconds after the Big Bang, separated electromagnetism from the weak nuclear force and is responsible for particles acquiring mass through the Higgs mechanism. The strong nuclear force is believed to have separated from the electro-weak force at even earlier times. And gravity, described by general relativity, is thought to have unified with the other forces only at the Planck scale, before the Planck time. The specific way these phase transitions occurred determined the properties of the particles and forces we observe today. The masses of elementary particles, the strength of the electromagnetic coupling, the ratio of baryons to antibaryons that allowed matter to survive after the annihilation of matter and antimatter in the early universe. These are not arbitrary numbers. They are the outputs of the phase transitions that occurred in the first fractions of a second. And here is what makes this relevant to the question of what came before. The specific values of these numbers, the specific way the symmetries broke, may contain information about the conditions that preceded the Big Bang. If the universe underwent a period of extreme expansion called inflation before the standard Big Bang phase, that inflationary period would have left specific signatures in the distribution of matter and the temperature fluctuations of the cosmic microwave background. And if there were a universe or some structure before the Big Bang, the conditions of that predecessor might have influenced the initial conditions of inflation. The cosmic microwave background is therefore not just a snapshot of the universe at 380,000 years old. It is a message from the inflationary period that preceded the standard hot Big Bang. And that inflationary period may itself carry information about whatever came before it. In 1980, the physicist Alan Guth proposed a solution to several persistent puzzles in standard Big Bang cosmology. His proposal, called cosmic inflation, transformed our understanding of the early universe and opened a door to the question of what came before the Big Bang. The puzzles that inflation was designed to solve were collectively called the horizon problem and the flatness problem, along with several others. The horizon problem is this: the cosmic microwave background radiation, observed across the entire sky, has the same temperature in every direction to extraordinarily high precision, differing by only about 1 part in 100,000. This uniformity is extraordinary because, in the standard Big Bang picture, regions of the sky more than about 2 degrees apart were never in causal contact at the time the CMB was released. They were too far apart for light to have traveled between them in the time available. Yet they have the same temperature. How did they reach thermal equilibrium if they couldn't communicate? The flatness problem is related. The universe we observe is spatially flat to extraordinary precision. The total energy density of the universe is within about 0.5% of the critical density required for flat geometry. In general relativity, a flat universe is an unstable equilibrium. Any deviation from perfect flatness in the early universe would have grown over time. To be as flat as we observe today, the universe must have been extraordinarily flat at early times, to a precision of roughly 1 part in 10 to the 60. Why was the early universe so exquisitely fine-tuned to be flat? Inflation solves both problems in one stroke. The inflationary proposal is that the very early universe underwent a period of exponential expansion. driven by the energy density of a quantum field called the inflation field. During inflation, the universe expanded by a factor of at least 10 to the 26th, and possibly very much more. In an extraordinarily short time, a region of the universe that was smaller than a proton expanded to a volume larger than the observable universe today. During this expansion, any curvature of space was smoothed out, just as the surface of a balloon appears flatter as the balloon is inflated. This explains the flatness of the observed universe. And the region that inflated to become the observable universe was originally small enough that its different parts were in causal contact before inflation began, allowing them to equilibrate to the same temperature. This explains the uniformity of the CMB. But inflation did something else, something more profound and more relevant to our question tonight. Quantum mechanical fluctuations, tiny random variations in the energy density of the inflaton field, were stretched by inflation from quantum scales to cosmic scales. What were microscopic quantum uncertainties before inflation became macroscopic density variations after inflation? These density variations are exactly what later seeded the formation of large-scale structure in the universe, the galaxies, galaxy clusters, and cosmic web that we observe. The temperature fluctuations in the CMB, those tiny 1 in 100,000 variations that WMA P. and Planck measured with such extraordinary precision, are the stretched-out footprints of quantum fluctuations that occurred during inflation. And the specific pattern of these fluctuations, the way their amplitude varies with scale, carries information about the physics of inflation. This is one of the most remarkable things in science. We can read in the temperature map of the CMB the quantum mechanical fingerprints of a period of exponential expansion that ended approximately 10 to the minus 32 seconds after the Planck era. We are reading the handwriting of quantum mechanics from the first tiny fractions of a second of cosmic history. What is the inflaton field? This is a crucial question and one that remains unanswered. The inflaton is a hypothetical quantum field whose energy density drove the exponential expansion of inflation. Its detailed properties, its mass, its coupling to other fields, the shape of its potential energy function, are constrained by observations of the CMB. But its fundamental nature and its relationship to the other known quantum fields of particle physics are not established. Inflation is a framework, not a fully specified theory. There are dozens of specific inflationary models, each with different predictions for the detailed pattern of CMB fluctuations, and distinguishing between them observationally is an active area of research. What ended inflation? According to inflationary models, the inflaton field gradually lost energy density as it evolved toward a minimum of its potential energy function, a process called slow-roll inflation. When the inflaton field reached the minimum of its potential, its kinetic energy was converted to ordinary matter and radiation through a process called reheating. The energy that had been driving exponential expansion was transferred to the particles and fields of the standard model of particle physics. The universe was flooded with hot, dense matter and radiation. This moment of reheating is what most physicists mean when they refer to the Big Bang. It's not a singularity. It's the moment when the inflaton field finished driving inflation and converted its energy to ordinary matter and radiation initiating the hot Big Bang phase that we can describe in much greater detail. And this means that the question of what came before the Big Bang becomes, more specifically, the question of what came before inflation, or what drove inflation, or what set the initial conditions of the inflating field. These questions lead us into truly uncharted territory. One of the most startling implications of inflationary cosmology was discovered almost immediately after Guth's original proposal. It was worked out in detail by the physicists Paul Steinhardt, Alexander Vilenkin, and especially André Linde in the early 1980s. Inflation, once it starts, almost certainly doesn't stop all at once everywhere. Here is why. The inflated field drives inflation as long as it has high enough energy density to maintain the exponential expansion. Eventually, the field loses energy and reheating occurs, ending inflation locally and producing the hot Big Bang phase in that region. But the inflating field is a quantum field, and quantum fields fluctuate. In some regions of the inflating universe, quantum fluctuations kick the inflating field back up to higher energy densities, restarting or sustaining inflation in those regions, even as it ends in neighboring regions. The key insight is this. Because the expansion during inflation is exponential, the volume of space is increasing so rapidly that even though most of any given volume of inflating space eventually stops inflating and reheats, the inflating regions expand faster than they can be converted to non-inflating regions. Inflation creates more inflating space faster than it creates non-inflating space. The inflationary process, once started, never completely stops. Inflation goes on forever. Some regions transition to the hot Big Bang phase, cool, form galaxies, stars, planets, possibly life. Other regions continue to inflate. The inflating regions expand exponentially and continually spawn new regions that transition to the hot Big Bang phase. The process propagates indefinitely. This is called eternal inflation, and its implication is one of the most radical ideas in the history of cosmology. What we call the Big Bang, the moment when our observable universe transitioned from inflation to the hot Big Bang phase, was not the beginning of everything. It was a local event within an eternally inflating background. Our universe, the region we can observe, is a bubble within an eternally inflating sea. Other bubbles have formed elsewhere in the inflating background, before our bubble, after our bubble, and simultaneously with our bubble. Each bubble is its own Big Bang, its own expanding universe with its own subsequent evolution. There are, in this picture, infinitely many bubble universes. An eternally inflating background continuously spawning new bubbles, each one potentially different from the others because the quantum fluctuations that trigger bubble nucleation can produce different configurations of the inflating field in different bubbles, leading to different physical constants, different particle physics, possibly different laws of nature in different bubbles. This is the multiverse. The word multiverse has been used in many different contexts in physics and popular science, and not all of them are equivalent. The eternal inflation multiverse is the most direct and perhaps the most well-motivated theoretical prediction from established physics. It follows from two things: the framework of inflation, which is strongly supported by CMB observations, and quantum mechanics, which predicts that quantum fields fluctuate. Put these two together, and eternal inflation and the associated multiverse follow almost inevitably. The implications are both exhilarating and deeply troubling. If eternal inflation is correct, then the question of what came before the Big Bang has a specific answer. Before our Big Bang, there was the inflating background. Before the inflating background, there was whatever state gave rise to it. The inflating background had a beginning, or it didn't. If it had a beginning, what was before that? If it didn't have a beginning, has inflation been going on forever? And what does it mean for a physical process to have been going on forever? The Borde-Guth-Vilenkin theorem, proved in 2003 by Arvind Borde, Alan Guth, and Alexander Vilenkin, shows that any space-time that has been expanding on average throughout its history must have had a past boundary, a beginning. This theorem applies to eternally inflating space-times. Even if inflation goes on forever into the future, it cannot have been going on forever into the past. The inflating background had a beginning. What was the beginning of inflation? One of the most audacious proposals in cosmology is that the universe literally came from nothing. Not from a previous universe, not from an inflating background, not from any prior physical state. From a genuine quantum vacuum. This proposal is associated primarily with the physicist Alexander Vilenkin, who developed it in the early 1980s. The idea draws on a phenomenon in quantum mechanics called quantum tunneling. In classical mechanics, a particle cannot pass through a barrier if it doesn't have enough energy to climb over it. A ball rolling toward a hill will stop and roll back if it doesn't have enough kinetic energy to reach the top. This is intuitive, and it's how classical physics works. In quantum mechanics, particles can tunnel through barriers. Because of the wave-like nature of quantum mechanical objects, there is a non-zero probability of a particle being found on the other side of a classically impenetrable barrier, even without enough energy to climb over it. Quantum tunneling is not a metaphor or a thought experiment. It is measured, used, and essential. It's the mechanism by which nuclear fusion occurs in the sun at temperatures and pressures that would classically be insufficient. It's the mechanism behind radioactive alpha decay. It's the operating principle of tunnel diodes used in electronics. Quantum tunneling is real. Vilenkin's proposal applies the concept of quantum tunneling to the universe itself. The universe, in this picture, can be described by a quantum wave function. This is the wave function of the universe, a concept developed formally in the 1960s and 1970s by Hugh Everett, Bryce DeWitt, and John Wheeler, and applied to cosmology by James Hartley and Stephen Hawking in their famous no-boundary proposal. The idea is that the universe could have tunneled into existence from literally nothing, not from a quantum vacuum of existing space-time, which would still be a something. From a mathematical state of literally nothing, no space, no time, no energy, no quantum fields. And through quantum tunneling, a universe with a small but finite size could have spontaneously come into existence. The probability of this tunneling event is not zero. In quantum mechanics, as long as the probability is not exactly zero, the event can happen. And in some sense, asking why the universe exists at all becomes the question of why the tunneling event happened. And the answer is, because in quantum mechanics, everything that can happen does eventually happen, given enough time, except that in this case, there was no time before it happened. And time was one of the things that came into existence when it happened. This is the point where language starts to fail us. The concept of cause and effect requires time. Event A causes event B means A happens before B. If there is no time, there is no before and after. And the concept of causation, in its ordinary sense, becomes meaningless. Vilenkin's proposal, and the related Hartley-Hawking no-boundary proposal, suggest that the universe had no boundary in time. That asking what came before the beginning is like asking what's south of the South Pole. Not that the answer is nothing, but that the question presupposes something, a time before time, that doesn't exist. The Hartley-Hawking no-boundary proposal, developed by James Hartley and Stephen Hawking in 1983, uses a mathematical technique called the path integral formulation of quantum gravity. In this approach, the probability of the universe having a particular configuration today is calculated by summing over all possible histories of the universe, weighted by a quantum mechanical amplitude. The proposal specifies a particular boundary condition, the no-boundary condition, which says that the universe has no boundary in the past. Time becomes space-like at the beginning, meaning the distinction between time and space dissolves, and there is no singular beginning point, just as there's no edge to the surface of a sphere. In this picture, asking what happened before the Big Bang is answered by saying that the question is malformed. Time, as a meaningful dimension with a clear before and after, emerges from the quantum gravity era. Before that, time was not a well-defined concept. The universe didn't come from anything because the concept of coming from requires a temporal precedence that doesn't exist in the quantum gravity regime. This is not a comfortable answer. It is, in many ways, the most honest answer, and it leaves many people more unsettled than a simple nothing would have. If the no-boundary proposal seems too abstract to satisfy, there is a class of alternatives that posit something quite concrete as preceding our universe. These are cyclic cosmologies, models in which the Big Bang was not the absolute beginning of everything, but was instead a transition from a previous state of the universe, or a previous universe entirely. Cyclic cosmologies have a long history in human thought. The idea that the universe undergoes repeated cycles of creation and destruction appears in Hindu cosmology, in the cosmologies of various ancient cultures, and has been a recurring theme in philosophical speculation throughout history. But cyclic cosmologies also have a serious modern scientific incarnation supported by detailed mathematical models and, at least partially, by observational constraints. The most developed modern cyclic cosmology is the ekpyrotic model, and its descendant the cyclic model, developed primarily by Paul Steinhardt and Neil Turok in the early 2000s. These models draw on ideas from string theory and M theory, the framework that attempts to unify all the forces of nature, including gravity, in a higher dimensional mathematical structure. In M theory, the universe we experience in three spatial dimensions may be a three-dimensional surface called a brane, embedded in a higher dimensional space. Other branes may exist in this higher dimensional space, parallel to ours, separated by distances in the extra dimensions that may be microscopically small. These other branes are effectively other universes, invisible to us because the particles and forces we're made of are confined to our brain and cannot propagate into the extra dimensions, though gravity can. The ekpyrotic model proposes that our universe's Big Bang was caused by the collision between two such brains. Two three-dimensional universes, parallel to each other in the extra dimension, approached each other and collided. The kinetic energy of the collision was converted to matter and radiation in both brains at the moment of impact. Our Big Bang was a collision. The collision was not destructive in the catastrophic sense. It was more like two surfaces being pressed together and then bouncing apart. The energy of impact created the hot, dense state we call the Big Bang. The universes then expanded and cooled. Eventually, some combination of factors causes the brains to begin approaching each other again, and the cycle repeats. In the cyclic model, developed by Steinhardt and Turok as a refinement of ekpyrosis, the universe goes through an endless sequence of Big Bang, expansion, cooling, structure formation, and then a slow contraction back toward the next collision. The large-scale structure of the universe, the accelerating expansion driven by dark energy, is a feature of the cyclic model's current phase, and eventually dark energy will cause the energy conditions of the universe to change in a way that initiates the contraction phase, leading to the next bounce. The cyclic model is compelling in several ways. It naturally explains the flatness, horizon, and homogeneity problems that inflation was designed to solve, but through a different mechanism. The universe had effectively infinite time to equilibrate in previous cycles. It predicts a specific pattern of gravitational waves from the early universe that is different from the pattern predicted by simple inflationary models, allowing the two frameworks to be distinguished observationally in principle. But the cyclic model also faces serious challenges. How does the transition from contraction to expansion actually work physically? What prevents the singularity from being a true singularity, from being genuinely ill-defined? Does information from the previous cycle survive the bounce, or does each cycle begin with a clean slate? These questions don't have completely satisfying answers within the current formulation of the model. Roger Penrose's conformal cyclic cosmology, or CCC, is a different approach to the cyclic universe idea. Penrose proposes that the remote future of our universe, when all black holes have evaporated through Hawking radiation and all massive particles have decayed, becomes conformally equivalent to the Big Bang of a new universe. In Penrose's picture, the distinction between extraordinarily large scales and ordinarily small scales disappears in a universe containing only massless particles, because massless particles don't have a natural scale. This scalelessness means that the very remote future of one universe can be identified with the very beginning of the next universe, and the sequence continues indefinitely. Penrose's CCC has made specific observational predictions, claiming that anomalous circular patterns in the CMB could be remnants of events in the universe preceding ours, perhaps the mergers of supermassive black holes in the previous aeon. These claims have been disputed by other cosmologists, who argue that the patterns claimed by Penrose and his collaborators can be accounted for by standard cosmological processes without invoking a previous aeon. The debate is ongoing. What cyclic cosmologies share is the proposal that before was another version of the universe. Not our universe in the past, but a predecessor universe, or an earlier cycle of our own universe, or a previous aeon. The Big Bang was not the beginning of existence. It was a transition, a bounce, a collision, a recycling of a pre-existing universe into a new one. This is more concrete than the no-boundary proposal. It posits something before the Big Bang. But it raises the obvious question: what was before the first cycle? If the cycles have been going on forever, does an infinite past make sense? If they haven't been going on forever, what started the first cycle? The Borda-Guth-Vilenkin theorem applies to many cyclic models as well. If the universe has been expanding on average throughout its history, it must have had a past boundary. Some cyclic models are specifically designed to evade this theorem by having cycles that contract as well as expand, with no net expansion over many cycles. But whether these models are truly past eternal, or whether they too require an initial condition, is a subject of ongoing research. String theory, or its most complete current formulation, M theory, offers a very different perspective on the question of what came before, and not a specific model for a pre-Big Bang state, but a framework within which many different things could have come before, or within which the question takes on a very different character. String theory is the attempt to describe all the fundamental particles and forces of nature as different vibrational modes of one-dimensional objects called strings, rather than as point particles. The strings vibrate in 10 or 11 dimensions, most of which are compactified, curled up at scales so small as to be unobservable by any current or foreseeable experiment. The specific shape in which the extra dimensions are compactified determines the effective physics in the 4 large dimensions we observe. Different compactifications give different values for the physical constants, different particle physics, different low-energy laws of nature. And string theory admits an astronomically large number of different possible compactifications. Current estimates suggest that the number of distinct string theory vacua, the number of different ways the extra dimensions can be arranged, is approximately 10 to the 500. That is a 1 followed by 500 zeros. This enormous collection of possible universes is called the string theory landscape. The landscape is relevant to the question of what came before, because it provides a context for eternal inflation that is even more radical than simple eternal inflation. In the landscape picture, different regions of the eternally inflating background do not just transition to the hot Big Bang phase at different times. They transition to different points on the landscape, different vacuum states with different physical constants, different particle physics, different values of the cosmological constant. Our universe, with its specific physical constants and laws, occupies one particular point on the landscape. The reason it has the specific properties it does, rather than any of the other 10 to the 500 possible sets of properties, might be explained anthropically. Only certain ranges of physical constants allow the formation of stars, planets, and observers, so observers will always find themselves in a universe with those properties, regardless of how many other vacua exist. This is the anthropic principle applied to the landscape. The landscape and the anthropic principle have been deeply controversial since they were proposed. Many physicists find them unsatisfying because they seem to abandon the goal of explaining why our universe has its specific properties from first principles. If the answer to why the electron has the mass it does is that it had to have some mass in a specific range to allow atoms to exist and for us to ask the question, that feels less like an explanation and more like a tautology. But others argue that this discomfort is simply the discomfort of confronting a new kind of explanation. That in a universe with 10 to the 500 possible vacua and a mechanism to realize many of them through eternal inflation, the anthropic principle becomes a genuine scientific prediction rather than a philosophical evasion. For our question tonight, the landscape picture transforms what came before. What preceded our Big Bang was not another universe with the same laws of physics. It was the inflating background and the quantum tunneling event that selected our specific vacuum from the landscape. The predecessor state is an inflating sea of possible physics. And our Big Bang was the moment when our particular bubble of stable vacuum nucleated within that sea. This is a before that is genuinely alien in character. It is not a place with stars and galaxies. It is not a universe that looks anything like ours. It is an inflating quantum foam of unstable false vacuum, seething with quantum fluctuations, producing bubble universes with wildly different physical constants, most of which would be immediately hostile to any kind of complexity or structure. We exist in one of the rare bubbles that happen to have the right properties. And the sea from which we emerged, from which all the bubbles emerge, goes on forever. While string theory approaches the question of quantum gravity through higher dimensions and extended objects, an entirely different approach called loop quantum gravity attempts to quantize space-time directly without introducing extra dimensions or extended objects. Loop quantum gravity, developed primarily by Abhay Ashtekar, Lee Smolin, and Carlo Rovelli in the 1980s and 1990s, proposes that space itself has a discrete structure at the Planck scale. Just as matter is made of discrete quanta, atoms and particles, space is made of discrete quanta of geometry, called spin networks. Time is similarly discrete. Space-time at the Planck scale is not a smooth continuum, but a granular network of quantum geometric elements. When loop quantum gravity is applied to cosmology, it produces what is called loop quantum cosmology, or LQC. And the central result of LQC is remarkable. The Big Bang singularity is replaced by a big bounce. In classical general relativity, running the universe's expansion backward leads to a singularity, a point of infinite density and curvature where the equations break down. In loop quantum cosmology, the discrete structure of space at the Planck scale provides a quantum mechanical repulsion at extremely high densities. When the density of the universe reaches the Planck density, approximately 5 times 10 to the 96 kilograms per cubic meter, the quantum geometric effects create a repulsive force that counteracts gravitational attraction and prevents the singularity from forming. Instead of collapsing to a singularity, the universe bounces. It reaches a minimum volume, a maximum density, and then expands again. The Big Bang becomes the big bounce. Our expanding universe emerged from a previously contracting universe that reached maximum compression and bounced outward. This is a concrete and mathematically well-defined answer to what came before. Before the Big Bang was a contracting universe. Our universe did not begin from nothing. It began from a compressed predecessor state, a universe that was contracting rather than expanding, that reached maximum density and bounced into our current expanding phase. What was that contracting universe like? Was it our universe in a previous cycle, expanding for billions of years and then recollapsing? Or was it a structurally different kind of universe? Did it contain matter, galaxies, stars, possibly life? These questions depend on the details of the bounce and whether information from the pre-bounce phase survives through the bounce into our phase. Initial calculations in loop quantum cosmology suggested that most information from the pre-bounce phase is scrambled by the extreme conditions at maximum compression. The post-bounce universe starts in a nearly thermal state, with the specific properties of the pre-bounce universe washed out. If this is correct, we could never determine observationally what the pre-bounce universe was like. And in a certain sense, the big bounce marks a kind of functional beginning, even if it's not an absolute beginning. More recent research has challenged this view, suggesting that some information from the pre-bounce phase may survive in subtle imprints on the post-bounce universe's density fluctuations. Specifically, some loop quantum cosmology models predict specific signatures in the CMB, deviations from the standard inflationary predictions that could be detected by future CMB experiments with sufficient sensitivity. If these signatures are observed, it would provide the first observational evidence for a pre-Big Bang state. Loop quantum cosmology also faces challenges. The full theory of loop quantum gravity, from which loop quantum cosmology is derived through approximations and symmetry assumptions, is still under development. The specific predictions of LQC depend on choices made in the approximation scheme, and different choices can lead to different predictions. The mathematical consistency of the full theory is still being worked out. But loop quantum cosmology provides the most concrete and mathematically explicit answer currently available to the question of what came before. Before the Big Bang was a contracting universe. Before that contracting universe was a previous big bounce, a previous expanding phase that contracted. And before that, perhaps, another bounce and another expanding phase. The universe could have been cycling through bounces forever. Or the sequence could have had a first bounce at some point, requiring an additional explanation for what initiated it. Let's step back from the specific physical models and confront the philosophical core of the question. Because there is a sense in which all of the scientific answers we've discussed, the no-boundary proposal, eternal inflation, the cyclic universe, the big bounce, all of them eventually run into the same wall. They all require explanation. They all have preconditions. They all shift the question rather than answering it. If the universe quantum tunneled from nothing, why was there a quantum mechanical rule allowing tunneling? Why was there a notion of probability at all? The laws of quantum mechanics themselves require explanation. If the universe is one bubble in an eternally inflating background, why does eternal inflation exist? What are the laws governing it? Where do those laws come from? If the universe bounced from a predecessor, what was the predecessor like? Where did it come from? If cycles have been going on forever, what does forever mean in the context of a universe that has been cycling without beginning? This is the regress problem. Every explanation requires a foundation. Every foundation requires an explanation. The question of ultimate origin is one that may, in principle, be unanswerable. Not because we're not smart enough to find the answer, but because the question may have no answer of the type we're looking for. Because the universe may simply be without an explanation for why it exists rather than not existing, or with an explanation that is itself unexplained. Gottfried Wilhelm Leibniz, the 17th century philosopher and mathematician who co-invented calculus alongside Newton, asked what he called the fundamental question of metaphysics. Why is there something rather than nothing? This question predates modern cosmology by 3 centuries, but it remains the core question. And modern cosmology has not answered it. Modern cosmology has shown us that the something that exists is vastly larger and stranger than anything Leibniz imagined. But the question of why anything exists at all, rather than the simplest possible state of all, which is nothing, has not been answered. David Hume, the 18th century Scottish philosopher, argued that causation is itself a concept derived from experience, from seeing one thing follow another in time. If there is no time before the universe, there is no causation before the universe. And asking for a cause of the universe is asking for something the concept of causation is not equipped to provide. Immanuel Kant argued that questions about the beginning of the universe in time are what he called antinomies, questions that can be argued with equal validity in both directions, suggesting that the question itself may be beyond the capacity of pure reason to resolve. Modern physics has added precision to these philosophical puzzles without eliminating them. We can calculate with considerable specificity what the universe looked like 1 second after the Big Bang. We can see in the CMB the structure of the universe at 380,000 years. We can trace the universe's evolution with remarkable precision across 13.8 billion years of history. We can describe, in theoretical terms, the physics of inflation and its role in setting the initial conditions for the hot Big Bang. But the question of why there is a universe at all, rather than nothing, remains. And it remains for a reason that should be taken seriously. It may not have an answer in the terms we're used to asking questions. This is not a defeat. It is an honest statement about where the frontier of understanding currently lies. There is one more layer of complexity in the question of what came before that we haven't fully addressed. It has to do with the nature of time itself. Time, as we experience it, has a direction. The past is fixed and the future is open. Causes precede effects. Entropy increases. Things fall apart, don't spontaneously assemble. The universe evolves from more ordered states to less ordered states, from lower entropy to higher entropy. This is the second law of thermodynamics, and it gives time its arrow. But the fundamental laws of physics, at the deepest level, are almost completely time-symmetric. The equations of classical mechanics, quantum mechanics, electromagnetism, the strong and weak nuclear forces, and general relativity all have solutions that run equally well forward and backward in time. A movie of any fundamental physical process, run in reverse, obeys the same laws as the original. The one exception is the weak nuclear force, which exhibits a tiny asymmetry called CP violation. But this asymmetry is too small to explain the overwhelming arrow of time we experience. The arrow of time that we experience, the reason the past is different from the future, comes not from the fundamental laws, but from the initial conditions of the universe. The universe began in an extraordinarily low entropy state. The Big Bang produced a universe of remarkable order. As the universe evolved, entropy increased, And that increase in entropy is what we experience as the flow of time from past to future. But this raises a deep question. Why did the universe begin in such a low entropy state? Why was the initial condition of the universe so ordered? Statistical mechanics would suggest that the most likely state is one of high entropy, not low entropy. High entropy states vastly outnumber low entropy states. If the initial conditions of the universe were chosen randomly from all possible initial conditions, the overwhelming probability would be that the universe started in a high entropy state. And yet it didn't. This is sometimes called the past hypothesis, the assumption that the universe began in an extraordinarily low entropy state. And explaining the past hypothesis is one of the deepest problems at the intersection of physics and philosophy. Some cosmologists argue that the past hypothesis can be explained by the specific nature of the Big Bang, that the quantum state of the early universe naturally produced low entropy in a way that can be calculated. Others argue that the past hypothesis is itself the fundamental brute fact about the universe, the unexplained given from which everything else follows. Still others argue that the past hypothesis is explained by the anthropic principle. Observers can only exist in regions of the universe with a sufficiently long period of low entropy to allow complexity to develop. So observers will always find themselves in a post-Big Bang epoch of entropy increase. The arrow of time also affects what we mean by before. If time is a physical thing with a direction, and if the direction of time is determined by the entropy gradient set by the initial conditions of the universe, then what does before mean in a context where there are no initial conditions? If there were a contracting pre-bounce universe, did time in that universe run in the opposite direction from ours? Were there observers in that universe who experienced time running toward what we call the Big Bounce and considered it their future? These questions don't have answers yet, but they illustrate how deeply the question of what came before is entangled with the most fundamental questions about the nature of time, causation, and physical law. All of the theoretical frameworks we've discussed are fascinating and profound. But science is ultimately an empirical discipline. The question is not just what the theories say, but what we can observe, test, and confirm. What observational evidence do we have, or could we have, about what came before the Big Bang? The cosmic microwave background is our primary source of information about the early universe, measured with extraordinary precision by the WMAP and Planck satellites. The CMB has confirmed the standard hot Big Bang model and the basic framework of inflation. The spectrum of temperature fluctuations, the statistical pattern of hot and cold spots across the sky, agrees with the predictions of the simplest inflationary models to remarkable precision. But the CMB also contains potential signatures of what came before inflation. Loop quantum cosmology predicts specific modifications to the large-scale power spectrum of CMB fluctuations, deviations from the standard inflationary prediction at the largest angular scales. The Planck satellite data does show an anomaly at large angular scales, a deficit of power compared to the simplest inflationary predictions, that some researchers have argued could be a signature of a pre-inflationary phase or a pre-bounce state. However, the statistical significance of this anomaly is disputed, and it could also be explained by standard cosmological processes or by observational systematics. Conformal cyclic cosmology, Roger Penrose's model, predicts specific circular patterns in the CMB, the remnants of gravitational wave signals from the final evaporation of black holes in the previous aeon. Penrose and his collaborators claim to have found these patterns in the Planck data. But other cosmologists have analyzed the same data with different methods and concluded that the claimed patterns are not statistically significant above what would be expected from a standard cosmological model. Primordial gravitational waves would be one of the most powerful probes of the inflationary period. During inflation, quantum fluctuations in the gravitational field itself were stretched to cosmic scales, just as the density fluctuations were. These gravitational waves from inflation would leave a specific imprint on the polarization of the CMB, called B-mode polarization, that could be measured by sensitive polarization experiments. The BICEP-2 experiment announced in 2014 that it had detected this B-mode polarization, which would have been a landmark confirmation of inflation. However, subsequent analysis showed that the signal could be entirely explained by polarized emission from dust within the Milky Way. The B-mode signal from primordial gravitational waves remains undetected. Current experiments, including the BICEP array and the Keck array, are continuing to search for it with increasing sensitivity. The detection of primordial gravitational waves would not only confirm inflation, but would provide information about the energy scale of inflation, the energy density of the inflaton field, when inflation was occurring. This energy scale determines which specific inflationary models are viable and provides constraints on what could have preceded inflation. Future space-based gravitational wave observatories, including LISA and the proposed Big Bang Observer, could detect gravitational waves from even earlier epochs of the universe, potentially including signals from the pre-inflationary era or from a pre-bounce contracting phase. The gravitational wave background is a potential window onto the earliest moments of cosmic history that the electromagnetic spectrum, including the CMB, cannot provide. Because gravitational waves decouple from matter much earlier than photons do. The detection of neutrino background, the cosmic neutrino background that decoupled from matter at about 1 second after the Big Bang, is another potential probe of the early universe. While we have not yet directly detected individual cosmic background neutrinos, their gravitational effects have been observed in the CMB. Future experiments may be able to detect them directly, providing information about the universe at 1 second of age. The bottom line is this: we currently have no direct observational evidence for any specific pre-Big Bang scenario. The CMB data is consistent with the standard inflationary picture without requiring a pre-inflationary phase. The anomalies that have been reported are disputed and could have mundane explanations. This does not mean that there was nothing before the Big Bang, or that we will never have evidence bearing on the question. It means that the question is currently at the frontier of what observation can reach. Planned experiments over the next 1 to 3 decades, measuring CMB polarization with unprecedented sensitivity, detecting primordial gravitational waves, potentially observing signatures from quantum gravity effects in the early universe, may push the observational frontier closer to the beginning and provide the first empirical constraints on pre-Big Bang physics. We are not yet there, but we are approaching it. Stephen Hawking spent much of his career thinking about the question of what came before the Big Bang. His answers evolved over the decades, and his final position is worth understanding carefully because it represents one of the most sophisticated attempts to address the question. Hawking's early position, developed with James Hartley in the no-boundary proposal of 1983, was that the question of what came before the Big Bang is literally meaningless, because time itself began with the Big Bang, or in the quantum gravity era immediately preceding it. The no-boundary condition specifies that the universe has no initial boundary, no edge in time, just as the surface of a sphere has no edge in space. There is no before the Big Bang in the no-boundary picture, because time as a well-defined dimension only emerged from the quantum gravity fog of the Planck era. In A Brief History of Time, published in 1988, Hawking used a famous analogy. Asking what came before the Big Bang is like asking what's south of the South Pole. The question sounds meaningful, but the concept of south runs out at the South Pole. There is no south of the South Pole. Similarly, time runs out at the beginning of the universe, and there is no before the beginning. But Hawking's position became more nuanced in later years. In The Grand Design, published with Leonard Mlodinow in 2010, Hawking argued that the universe could have spontaneously come into existence from nothing through quantum processes, without requiring a creator or a pre-existing state. He argued that the laws of physics themselves, specifically the law of gravity and the quantum theory, are sufficient to explain why there is something rather than nothing. The argument goes like this. In quantum mechanics, virtual particle pairs can spontaneously appear from the vacuum and then annihilate. This happens constantly in the quantum vacuum. Now, the total energy of the universe may be zero. The positive energy of matter and radiation is exactly cancelled by the negative gravitational potential energy. A universe with zero total energy can appear spontaneously from a quantum vacuum with zero energy, consistent with energy conservation. This argument is provocative, but has been criticized on several grounds. Most importantly, the quantum laws that allow this to happen still require explanation. Where do the laws of quantum mechanics come from? Why is there a quantum vacuum rather than truly nothing? The quantum vacuum of quantum field theory is not nothing. It's a sophisticated mathematical structure with specific properties. Hawking's response to this was that the laws of physics don't require a designer or creator. They are not imposed on the universe from outside. They are descriptions of patterns in the universe's behavior that emerge from the structure of the universe itself. In Hawking's view, the laws of physics are not separate from the universe, but are part of it. This is a philosophically interesting position, but it doesn't fully resolve the question. Even if the laws of physics are internal to the universe, they still appear to have specific mathematical forms that require explanation. Why these laws and not others? Why mathematics at all? In his final paper, published posthumously in 2018, Hawking and his collaborator Thomas Hertog proposed what they called a top-down cosmology. Rather than thinking of the history of the universe as a single deterministic trajectory from the Big Bang to the present, they proposed thinking of it using the sum over histories formulation of quantum mechanics, where all possible histories contribute to the current state of the universe, weighted by quantum mechanical amplitudes. The no-boundary condition specifies which histories contribute significantly. In this picture, there is no single prehistory of the universe. There are many possible histories, and what we observe today is determined by the sum over all those histories consistent with our current observations. The question of what came before the Big Bang doesn't have a single answer because there is no single history. There are many possible histories, and the universe's prehistory is fundamentally quantum and uncertain in a way that goes beyond ordinary quantum uncertainty. This is Hawking's most mature answer to the question, and it is, in many ways, the most honest. The universe's prehistory is not a definite classical history that we can in principle discover if we know enough. It is quantum mechanical, fundamentally probabilistic, and not fully specifiable even in principle. The before is not hidden from us by our ignorance. It is genuinely indeterminate in a fundamental quantum sense. One framework that has a surprising relevance to the question of what came before is the many worlds interpretation of quantum mechanics, developed by Hugh Everett in 1957. In the standard Copenhagen interpretation of quantum mechanics, a quantum system exists in a superposition of possible states until it is observed, at which point the wave function collapses to one definite outcome. The mechanism and meaning of this collapse have been deeply controversial since quantum mechanics was first formulated. And the Copenhagen interpretation essentially avoids the question by treating the collapse as a primitive fact. Everett proposed an alternative. Instead of the wave function collapsing when a measurement is made, the wave function never collapses. All possible outcomes of every quantum measurement actually occur, each in a separate branch of the universe's wave function. The wave function evolves deterministically according to the Schrödinger equation at all times. What we experience as the collapse of the wave function is actually the branching of the universe into multiple copies, one for each possible outcome. In the many worlds interpretation, the universe's wave function contains all possible outcomes of all quantum measurements simultaneously. Different branches of the wave function describe different histories of the universe. Applied to cosmology, the many worlds interpretation suggests that the beginning of the universe was not a single event with a single outcome. It was a quantum event with all possible outcomes, all possible initial configurations, all possible universes. Our particular universe, with its specific initial conditions and subsequent history, is one branch of this universal wave function. The question of what came before the Big Bang, in this context, becomes the question of how the initial quantum state of the universe was specified. If the universe's wave function was in some particular initial state that then evolved into the current state with all its branches, what specified that initial state? The no-boundary condition, the Hartley-Hawking proposal, is one attempt to specify this initial state. The tunneling proposal of Vilenkin is another. The many worlds interpretation also connects to the eternal inflation multiverse. Each bubble universe in the eternally inflating background can be thought of as a branch of the universal wave function. The multiverse and the many worlds interpretation converge on a similar picture. A vast quantum mechanical structure containing all possible universes, with our observable universe being one specific realization of one specific set of quantum outcomes. The question of what came before in this enlarged framework is the question of what set the initial wave function of this entire quantum multiverse. And here, the regress truly becomes vertiginous. If the wave function of the multiverse has an initial state, where did it come from? If it doesn't have an initial state, if it's been evolving eternally, what is the meaning of an eternally evolving quantum state? These questions take us to the very edge of what current physics can say. Beyond that edge lies genuine mystery. There is one more aspect of the question of what came before that needs addressing. And it connects the abstract physics to a question that many people find more personally compelling. The universe appears to be fine-tuned for the existence of life. The physical constants that determine the structure of matter and the strength of the forces, the speed of light, Planck's constant, the gravitational constant, the masses of the elementary particles, the strength of the electromagnetic force, the strength of the nuclear forces, appear to be set to values within very narrow ranges that permit the existence of atoms, molecules, stars, planets, and living things. Change the strength of the strong nuclear force by a few percent, and either atoms cannot exist or the proton is unstable. Change the cosmological constant, the energy density of empty space, by a factor of 10 to the 120 from the value it would naturally take from quantum field theory estimates. And the universe either collapses immediately or expands so rapidly that matter never forms. Change the ratio of the electromagnetic force to gravity by a small amount, and stars cannot exist. Change the ratio of matter to antimatter produced in the Big Bang by a tiny fraction, and the entire universe annihilates in the first second. The universe seems, in some sense, to have been set up precisely to allow our existence. This apparent fine-tuning is one of the most discussed puzzles in physics. There are essentially three families of response to this fine-tuning. The first response is that the fine-tuning reflects the existence of a designer. This is the approach of intelligent design and of theistic cosmology. The constants are not random because they were chosen. This is a coherent position, but it is not a scientific explanation in the sense of offering a mechanism or making testable predictions. It shifts the explanation to an entity outside the scientific framework. The second response is the multiverse plus anthropic selection. If there are vastly many universes, each with different values of the physical constants drawn from the string theory landscape or from the quantum fluctuations of eternal inflation, then most universes will have constants unsuitable for life. But the ones where observers exist will always find themselves in universes with constants compatible with their existence. We observe our constants not because they were designed, but because we can only exist where the constants permit life. This is a scientific response in the sense that it follows from established physics, inflation, and string theory, and is in principle testable, though the specific predictions are extremely difficult to test observationally, given that we can't access other bubbles. Critics argue that it makes too many untestable assumptions and that it explains too much by making the landscape so large and flexible that almost any observation is compatible with it. The third response is that the fine-tuning problem is an artifact of our ignorance. When a deeper theory is found that unifies gravity with quantum mechanics, it may turn out that the physical constants are not arbitrary parameters, but are determined by the structure of the theory. The way the compactification of the extra dimensions works out. In a complete, mathematically consistent theory of quantum gravity, perhaps there is only one possible set of physical constants, and the apparent fine-tuning is simply what that one set of constants looks like from our perspective. This would be the most satisfying scientific resolution. It would mean that the universe's properties are not fine-tuned at all, but are uniquely determined by the deepest principles of physics. But we don't know if this is true, and the string theory landscape, with its 10 to the 500 vacua, currently suggests that a unique determination is not the right picture. The fine-tuning problem is relevant to our question, because whatever came before the Big Bang must account for it. If our universe was selected from an ensemble by anthropic reasoning, then what came before is the ensemble itself. If our universe's constants are uniquely determined by the laws of physics, then what came before must be described by those laws. If the constants were designed, then what came before was the designer. Each answer points to a different picture of what preceded the universe we inhabit. We've traveled far tonight. From the Big Bang singularity to inflation, from eternal inflation to the multiverse, from the cyclic universe to the big bounce, from the no-boundary proposal to the many worlds interpretation, from quantum tunneling from nothing to the landscape and fine-tuning. We've spent time with Hawking, Vilenkin, Hartley, Penrose, Steinhardt, Turok, Linde, Guth. Let's be honest about where we actually are. We know, with high confidence, that the universe has been expanding and cooling for approximately 13.8 billion years. We know that it was once extremely hot and dense. We know that the cosmic microwave background was released about 380,000 years after the Big Bang, and has been traveling toward us since then, carrying information about conditions at that time. We know that Big Bang nucleosynthesis, occurring in the first minutes, produced the observed abundances of hydrogen, helium, and lithium. These are not speculative. They are measured, confirmed, and robust. We know with considerable confidence that something like inflation occurred. The flatness and horizon of the observable universe, the spectrum of CMB fluctuations, and the scale invariant power spectrum of density perturbations are all explained by inflation and are difficult or impossible to explain without it. Inflation is not proven in the way that general relativity is proven, but it is strongly supported by the available evidence. We know that quantum mechanics is the deepest description of matter and energy we have, and that any description of the universe's origin must ultimately be a quantum mechanical description. Classical descriptions break down before we reach the beginning. We know that general relativity and quantum mechanics are incompatible in their current formulations when applied to conditions of extreme density and curvature, like those near the Big Bang singularity. We need a theory of quantum gravity to describe those conditions, and we don't have one that is fully worked out and tested. Everything else, the specific pre-Big Bang state, whether it was eternal inflation, a cyclic bounce, quantum tunneling from nothing, or something entirely different, is at the frontier of what we know. These are serious scientific proposals supported by mathematical models and some observational motivation. But they are not confirmed. They are speculative. They may be wrong. And the question of what came before the Big Bang may turn out to have an answer that none of the current proposals anticipate. Because the physics required to answer it goes beyond what we currently understand. This is the honest answer. We don't know what came before the Big Bang. We have ideas. We have mathematical models. We have theoretical frameworks that make predictions, some of which are in principle testable. We are actively working to test them. But the question remains genuinely open. And that openness, rather than being a source of frustration, should be a source of wonder. The most fundamental question about the nature of reality, about why there is something rather than nothing, about what the ultimate origin of the universe is, remains unanswered. It is the most important open question in science. Its resolution, when it comes, will be one of the greatest intellectual achievements in human history. We are alive at a time when this question is being seriously pursued with the best tools of human ingenuity, mathematics, observation, experiment, and theory. We may not live to see the answer. Our children may not live to see it. But the work is underway. There's something that happens when you truly sit with the question of what came before the Big Bang. Not when you hear the answers, which are fascinating and strange, but when you sit with the question itself before any answer arrives. The question attacks the deepest assumption most people carry through their lives without ever examining it. The assumption that things have reasons, that events have causes, that existence has an explanation, that if you go far enough back in the chain of causes and effects, you'll eventually find something that explains everything. The question of what came before the Big Bang challenges all of this. Because every answer leads to another question. Every explanation requires a foundation that itself requires explanation. The regress is genuinely vertiginous when you follow it honestly. And the honest conclusion, the one that physics is gradually forcing us toward, is that either the regress terminates in a brute fact, an uncaused cause, a self-existing foundation, or the regress continues without end, which raises its own profound questions. Or the concept of explanation itself breaks down at the boundary of the universe. Because explanation requires time and causation, and the universe is where time and causation begin. None of these options is comfortable. None of them lets you off the hook. The question of what came before the Big Bang is not a question with a satisfying resolution that leaves you feeling settled. It is a question that, when properly understood, opens an abyss. That abyss is not a problem with the universe. It's a problem with our expectations. We are pattern-seeking creatures who evolved to understand local, medium-scale phenomena, cause and effect, before and after, beginning and end. These are the cognitive tools we have. And at the boundary of the universe, at the question of ultimate origin, these tools reach their limits. Recognizing that limit is not defeat. It is precision. It is saying clearly, here is where human understanding currently stands. Here is where the territory extends beyond the map. Here is the genuine frontier. The people who are most comfortable with this question are the physicists who work on it every day. Not because they have answers that non-physicists don't have, but because they have internalized the experience of working at the frontier where the questions outnumber the answers, where the honest response to many questions is we don't know, and where that not knowing is the beginning of inquiry rather than the end of it. The question of what came before the Big Bang is not a question you answer and move past. It is a question you carry, a question that changes how you look at everything else. Because if the origin of the universe is genuinely mysterious, if the most basic fact about reality, that there is a reality, has no explanation within the current framework of human understanding, then the universe is deeper than our current concepts can reach. That should make everything look a little different. Every star you see is a piece of a universe whose origin is unknown. Every atom in your body is part of a process that began, perhaps, in a quantum fluctuation from nothing, or in a bounce from a previous universe, or in the bubble nucleation within an eternal inflationary sea, or in a way that no human has yet imagined. You are made of stuff whose ultimate origin is a mystery, and that mystery is not something we failed to solve. It is the frontier of everything we know. Let's return one more time to the first second, not to review the physics, but to appreciate what it means to stand at the edge of knowledge and look backward. The first second of the universe's history contains within it the transition from quantum gravity fog to the hot Big Bang, the end of inflation, the creation of all the matter and radiation that makes up everything we see, the annihilation of almost all the antimatter, the quark-hadron transition as quarks bound together into protons and neutrons, and the beginning of Big Bang nucleosynthesis that would create the hydrogen and helium from which the first stars formed. Each of these transitions is understood in broad outline by physics we have good theoretical control over and that is supported by observations. But each of them also occurred in conditions more extreme than anything we can reproduce in a laboratory. Even at the Large Hadron Collider, which recreates conditions comparable to a tiny fraction of a second after the Big Bang at energies far below the Planck scale. And before all of these transitions, before the first second, before the quark-hadron transition, before the electroweak phase transition, before reheating ended inflation, before the inflationary period itself, before whatever preceded inflation, lies the territory where the map runs out. We can trace the universe's history with confidence to very close to the beginning. We can calculate what it looked like at 1 second with high accuracy. We can calculate what it looked like at 1 minute, 1 hour, 1,000 years, 1 million years, 1 billion years, and today, with increasing precision as we have more observational data. But the very beginning, the moment of origin, the question of what preceded the quantum gravity era, remains genuinely unknown, not confidently unknown, where we know what we're missing and are confident we could fill it in with more data. Genuinely unknown, where we are not sure we have the right conceptual framework to even formulate the question correctly. The physicists working on this problem are not frustrated by this. They are energized by it, because it means there is something genuinely new to discover. Not just more data within an existing framework, genuinely new physics, new concepts, possibly new mathematical structures, the kind of discovery that changes how every subsequent generation of scientists thinks about the universe. We are, in this regard, at a historically extraordinary moment. The universe's origin is within scientific reach in the sense that we can formulate precise questions about it, develop mathematical models for different scenarios, and in some cases, make observational predictions. But it is not yet within scientific reach in the sense of being answered. The question is open. The work is underway. This is science at its most alive. Here is the final layer of the question, the one that most cosmology discussions stop short of addressing. Even if we answer what came before the Big Bang, even if we establish with certainty that there was an eternal inflation, or a cyclic bounce, or a quantum tunneling from nothing, or a pre-existing brain universe, the question doesn't stop. Because we can always ask, what came before that? What caused eternal inflation to begin? What set the initial state of the quantum wave function that permitted the tunneling? What set the initial conditions of the contracting universe that bounced into our Big Bang? What was the brain universe made of, and where did it come from? The regress continues, unless one of two things is true. Either there is a terminus, a self-explaining or uncaused foundation, something that exists necessarily without requiring a cause. Philosophers have called this a necessary being, something whose essence is its existence, something that could not fail to exist. Whether physics can ever identify such a terminus, or whether physics by its nature can only ever provide provisional explanations that rest on further foundations, is itself a profound question. Or the regress doesn't terminate. The chain of causes and explanations extends infinitely into the past, or infinitely into a space of logical dependencies, with no ultimate foundation. In this case, the question of ultimate origin has no answer, not because we don't know it, but because there is no ultimate origin. There is just an infinite chain. Both of these options are deeply strange to human intuition. We are accustomed to things having beginnings, to stories having starting points, to explanations bottoming out somewhere. The idea of an uncaused cause or an infinite regress both violate the intuition that there must be a clean answer somewhere. But physical reality is not obligated to respect human intuition. The universe does not owe us a satisfying story. The deepest truth about reality may be one that our evolved, pattern-seeking, narrative-constructing minds are structurally ill-equipped to fully grasp. That is the most terrifying implication of the question of what came before the Big Bang. Not that the answer is nothing, which would at least be simple, but that the answer may require concepts we don't have, frameworks we haven't built, mathematics we haven't invented. That the frontier of this question is not just at the edge of current knowledge, but at the edge of current knowability. We may be asking a question that requires not just more data or more calculation, but a genuinely new way of thinking about existence, time, causation, and reality. A revolution not just in physics, but in the very concepts we use to understand physics. That revolution may be coming. It may require another Einstein or something even further beyond what we currently do to bring it about. It may take 100 years. It may take 1,000. But it will come. Because this question, the deepest question ever asked, will not stay unanswered forever. The universe has given us minds capable of asking it. It has given us mathematics and physics and telescopes and particle accelerators and satellites and computers. It has given us 13.8 billion years of cosmic history to observe and analyze. It will, eventually, give us the answer. Tonight, you asked the most dangerous question in science, and the answer you found was not nothing. The answer was a collection of possibles, of maybes, of carefully hedged and mathematically precise and observationally motivated maybes. Eternal inflation, maybe. A big bounce, maybe. A quantum tunneling from a state that was itself not nothing, maybe. A brain-world collision, maybe. A no-boundary universe where the question has no valid referent, maybe. Each maybe is not ignorance dressed up as sophistication. Each maybe is the frontier of human knowledge. In the area where the most fundamental questions about existence are being pursued with the most powerful tools our civilization has ever developed. The honest answer to what came before the Big Bang is, we are working on it, seriously, with equations and telescopes and particle accelerators and pure mathematical reasoning. And we have found that the answer is not simple, not nothing, and not settled. We have found that time may have had a beginning, or may not. That the universe may have emerged from a predecessor, or from nothing, or from a quantum state that makes the word nothing meaningless. That inflation may have been eternal, generating an infinite multiverse of which our universe is one tiny part. That the Big Bang may have been a bounce from a contracting predecessor universe. That the laws of physics, as we know them, break down before we reach the moment of origin. And what lies beyond that breakdown is where the real question lives. This is more terrifying than nothing, because nothing is simple. Nothing is clean. Nothing would at least be a definite answer, even an answer that seems paradoxical. But the actual situation is vastly more complex than nothing. It is a quantum mechanical, possibly infinite, potentially multiverse-containing, possibly timeless, or possibly bouncing, fundamentally uncertain state of affairs from which our universe emerged by processes we are only beginning to understand. And we, conscious beings on a pale blue dot orbiting an unremarkable star in the outer spiral arm of one of 2 trillion galaxies in the observable universe, have asked the question, have chased it with mathematics, have built the instruments to observe the faint thermal afterglow of the universe's early history, have detected the ripples of space-time from merging black holes, have mapped the structure of the universe across billions of light years, have traced the history of cosmic evolution from 1 second after the beginning to 13.8 billion years later. We are the universe asking itself what it is. We are the universe wondering where it came from. That the answer is still incomplete does not make the asking any less extraordinary. Go outside tonight. Look up. The sky you see is 13.8 billion light years deep in every direction. The photons hitting your retina have been traveling since before the Earth existed. The atoms in your eyes were forged in stellar explosions, and the universe whose origin you're contemplating has been in existence long enough to produce minds capable of contemplating it. Whatever came before all of this was, it led here. To you, asking the question. To us, chasing the answer. That may be the most remarkable fact of all. Thank you for spending this time with me, exploring the deepest question ever asked. If this changed how you think about existence, about time, about where everything came from, please take a moment to like the video and subscribe to the channel. These explorations take real care to put together, and your support is what makes them possible. The universe began. We know that much. Everything before it is the question that defines the frontier of everything we know. Sleep well at the edge of the abyss.